In operating systems, a deadlock is when processes are blocked indefinitely. Each process waits for a resource held by another. Imagine 4 cars at an intersection, each waiting for the other. None can move, causing a complete halt. Deadlocks waste resources and halt operations. Understanding deadlocks is vital for robust OS design. Learn to prevent, detect, and recover from deadlocks. For a deadlock to occur, 4 conditions must be met simultaneously. These are known as the Kaufman conditions. Understanding them is crucial for preventing and detecting deadlocks. The first is mutual exclusion. A resource can only be held by one process at a time. The second is hold and wait. A process holding a resource requests another. The third is no preemption. A resource cannot be forcibly taken away. Lastly, circular wait. A circular chain of processes waiting for each other. Detecting deadlocks in a system is crucial for maintaining its stability and performance. There are 2 primary approaches to deadlock detection: continuous detection and periodic detection. Continuous detection involves constantly monitoring the system for potential deadlocks, while periodic detection checks for deadlocks at specific intervals. One common method for detecting deadlocks is the use of resource allocation graphs. In this approach, a graph is used to represent the system's resources and the processes holding or requesting them. Processes are depicted as circles, resources as squares, and the relationships between them as arrows. A directed arrow from a process to a resource indicates a resource request, while an arrow from a resource to a process signifies that the resource is held by that process. By analyzing the resource allocation graph, we can detect cycles. A cycle in the graph indicates a circular wait condition, which is a strong indicator of a potential deadlock. Another method is to maintain a matrix representing the allocation and request status of each resource and process. By analyzing this matrix, we can identify patterns that suggest a deadlock. Section 4. Recovering from deadlock situations. Once a deadlock is detected, the operating system must employ recovery techniques to resolve the situation and restore normal system operation. Several methods can be used, each with its own advantages and disadvantages. One common approach is process termination. Process termination involves terminating one or more of the deadlocked processes. This can be done selectively by identifying the processes that are least crucial to the system's operation, or by terminating processes in a prioritized order. While this method can be effective, it can also lead to the loss of data and disrupt ongoing tasks. Another technique is resource preemption. In this approach, resources are forcibly taken away from one or more of the deadlocked processes and allocated to other processes. This can help break the deadlock, but requires careful consideration to avoid creating new deadlocks or starving other processes of resources. Section 5. Illustrative examples of deadlocks. To better understand deadlocks, let's consider a few real-world examples. Imagine 2 people working on a document using a shared editing platform. Person A opens the document in edit mode, preventing anyone else from making changes. Person B, unaware of this, also tries to open the document in edit mode. Now, both Person A and Person B are stuck, each waiting for the other to release the document. Another example is in a database system where multiple transactions are being processed concurrently. Transaction T1 might hold a lock on table A and request a lock on table B, while transaction T2 holds a lock on table B and requests a lock on table A. This scenario creates a classic deadlock situation where neither transaction can proceed. These examples highlight the importance of understanding and managing deadlocks. By being aware of the conditions that can lead to deadlocks, we can implement strategies to prevent them from happening in the first place. Section 6. Conclusion. The importance of deadlock management. Deadlocks pose a significant challenge in the design and operation of modern computing systems. From operating systems to database management systems and distributed environments, understanding and managing deadlocks is crucial for ensuring system stability, resource utilization, and overall performance. By carefully analyzing the conditions that lead to deadlocks, we can implement preventive measures such as resource allocation strategies and deadlock avoidance algorithms. Furthermore, robust deadlock detection and recovery mechanisms are essential for mitigating the impact of deadlocks when they do occur. Whether it involves process termination, resource preemption, or rollback mechanisms, choosing the appropriate recovery strategy depends on the specific context and the potential consequences of each action. As we move towards increasingly complex and interconnected computing environments, the importance of addressing deadlocks will only continue to grow.